Welcome to a special edition of AI Unraveled. I'm your co-host, Anna. Today's episode is brought to you by DjamgaMind. If you want this deep dive without the ads, check out our premium DjamgaMind feed. Today, we are looking at the execution layer. LLMs are great at writing emails, but how do you get them to run a company? We are comparing three radically different approaches to agentic AI: OpenClaw, AutoGPT, and n8n. One wants to do everything for you, one wants to talk you through it, and one forces you to draw the map yourself. We are analyzing the architectures, the token economics, and the security nightmares of handing over your API keys to a language model. Let's unravel the agentic war.
Back in 2024, giving an artificial intelligence, like a corporate credit card, root terminal access, and just total operational freedom, it sounded like the ultimate sci-fi future.
Oh, absolutely. The whole industry was obsessed with it.
Right. We were all obsessed with this idea of autonomous agents that could just figure things out on the fly. But here we are in 2026, and we've realized that unrestricted autonomy is actually, it's the fastest way to bankrupt your IT department.
And completely compromise your entire infrastructure while you're at it.
Exactly. The era of the blank check AI experiment is just dead. So today, we are performing a forensic, highly technical autopsy on what everyone is calling the Agentic Orchestration War.
Yeah, the fallout from those early kind of Wild West experiments forced a really brutal market correction.
It really did.
We are no longer just marveling at what a large language model can, theoretically achieve inside some pristine, heavily monitored laboratory setting. The conversation has violently shifted to enterprise production.
Which is exactly what we're dissecting today. We're looking at the battlefield dominated by three primary open source frameworks: OpenClaw, AutoGPT, and n8n.
Right.
Our objective for this deep dive is to basically tear these architectures down to the studs. And we're relying on this really comprehensive 2026 research report titled State Space Orchestration and the Inference Inflection. Plus, we have a stack of highly detailed architectural flowcharts to go through.
Yeah, and before we put the first framework on the table, we really have to establish the macro context of the ground we're standing on right now.
The foundation of the whole report.
Exactly. The report builds its entire thesis around this concept of the inference inflection. And for the IT strategists, the developers, or the CTOs listening to this deep dive, understanding this inflection point is the ultimate cheat code to surviving the modern token economy.
But the term itself, inference inflection, it feels a bit dense, right? Walk us through the actual mechanics of this macroeconomic shift. Like, how is 2026 fundamentally different from that massive generative AI boom we saw in 2023?
Well, the difference lies entirely in where the capital is burning.
Okay.
If you look back at that 2023 through 2025 window, the industry was completely defined by massive capital expenditure, CapEx.
Right, the hyperscalers and frontier labs incinerating billions of dollars.
Exactly, incinerating billions, building these massive GPU clusters just to train the foundational models. That was the era of building the brains. The primary bottleneck was compute availability for training runs that literally lasted months.
Yeah, the narrative back then was all about parameter counts and training data. You buy 50,000 specialized chips, lock them in a data center, feed them half the internet, and just wait.
But that paradigm is over. We have the models now.
And they're good.
They are highly capable. So the market reality today is defined by operational expenditure, OpEx.
Right.
The primary cost of artificial intelligence is no longer training. It is the staggering, continuous cost of live, high-volume inference in production environments.
Meaning the day-to-day running of the models.
Exactly. We're talking about the moment-to-moment computational expense of keeping these massive neural networks loaded in VRAM, processing user inputs, generating tokens, and executing logic across thousands of enterprise endpoints simultaneously.
And this demand is skyrocketing, mostly because of the shift towards sovereign AI, right? Like localized on-premise AI factories.
Oh yeah. Every Fortune 500 company suddenly realized that piping their proprietary, highly sensitive internal data to a public API endpoint was just a massive security liability.
A total nightmare for legal and compliance.
So they're pulling these models in-house. They want their own continuously running intelligence. But running a 100 billion parameter model, 200 weeks of it on your own hardware, or even through a dedicated private cloud instance, it fundamentally changes your operational math.
It changes everything about how you build software, honestly.
It does. Because when the primary cost is live inference, the most critical decision an engineering team makes is how the AI manages its state, how it routes its logic, and how it consumes computational resources.
So it's no longer just a minor IT optimization problem.
Not at all. It is a life or death corporate decision. If you choose the wrong orchestration framework, if you allow an AI to just burn tokens inefficiently, your project will bankrupt itself before it ever reaches scale.
Wow. Which means we really need to rigorously examine how these orchestration frameworks actually operate under the hood.
We do.
Because to understand what enterprises desperately need today, we first have to dissect what looked spectacular in a controlled demo, but catastrophically fails in the wild.
Right.
So we have to start with the maximalist approach, AutoGPT.
AutoGPT, the pure, unconstrained manifestation of the agentic dream.
The Wild West.
Exactly. The architecture here is officially categorized as autonomous goal-seeking, and the premise is incredibly seductive to anyone who wants to automate human labor.
Because you just give it a prompt and walk away, right?
Yeah, the human operator provides this abstract, high-level objective, and the framework assumes total, unconstrained control over the execution pathway required to achieve that state.
Let's use the specific visual example provided in the source material to kind of anchor this for everyone. The user input is simple. It's research competitors in the biotech space and generate a market analysis report.
A classic open-ended task.
Right. You hit enter and you walk away. The promise is that AutoGPT will just figure it out. But the mechanics of how it figures it out are incredibly complex.
Correct.
Because to navigate that vast, unstructured problem space, AutoGPT relies on a recursive self-prompting loop and an architecture called recap.
Yeah, recap. It stands for recursive context-aware reasoning and planning.
Okay, that's a mouthful.
It is, but mathematically, this is the engine attempting to decompose massive, ambiguous goals into executable tasks.
Right.
When AutoGPT receives that biotech prompt, it doesn't just start blindly Googling things. It uses recap to build a dynamic context tree.
So it maps it out.
Exactly. The root node of this tree is the primary goal. Then the AI queries itself to generate child nodes, which are the subtasks.
Like step 1, identify top 5 biotech firms.
Yes. Step 2, locate their most recent quarterly earnings reports. And then step 3, extract R&D spending.
I mean, it sounds highly logical on paper. It's breaking a massive problem into a hierarchical sequence of solvable micro-problems.
Right.
And it tracks its progress using this dynamic context tree, which theoretically allows it to use adaptive backtracking.
Theoretically, yeah.
Like if it goes down a rabbit hole trying to scrape a biotech website that is completely locked behind a paywall, it is supposed to recognize the failure, backtrack up the context tree, and just try a different node.
That is the theoretical math.
Right.
But here's where we have to apply the scalpel and look at the actual deployment telemetry.
Right, let's look at the reality.
To understand why this architecture implodes in a rigid corporate environment, we need to introduce the concept of state-space orchestration.
State space.
It's an engineering term.
Yeah.
It represents the complete multi-dimensional map of all possible configurations, data states, and external variables a system can encounter during execution.
So for a traditional piece of software, it has a very limited, heavily mapped state space. Like, if I write a Python script to pull data from a specific SQL database, there are only a few possible states.
Exactly.
The database connects, or it times out, the data is there or it isn't, the execution pathways are hard-coded.
AutoGPT, however, is designed to navigate an infinite unmapped state space blindly.
Wow.
It does not have a hard-coded map. It relies exclusively on the probabilistic nature of the large language model to guess the next right move through continuous criticism loops.
Guessing. That sounds risky.
It is. It takes an action, observes the chaotic result from the external environment, feeds that result back into its own context window, criticizes its own performance, and then formulates a new hypothesis.
Okay, the mechanics of that are actually terrifying from an enterprise perspective.
Oh, absolutely.
It sounds like giving a brilliant but profoundly amnesiac intern a corporate credit card, dropping them in the middle of a massive hedge fund server room, and just hoping they figure out the company's Q3 strategic roadmap purely by trial and error.
That amnesiac intern analogy perfectly captures what the researchers term the demo illusion.
This demo illusion.
Yeah, because in a highly controlled, tightly scoped 3-minute YouTube demo, AutoGPT looks like magic.
Right, you see those videos everywhere.
The demonstrator asks it to build a simple to-do list app, the environment is perfectly predictable, the APIs respond instantly, and the state space is tiny. The context tree holds up.
But when you deploy it against multi-step, deeply complex enterprise tasks like researching a volatile biotech market, the reality of the architecture kicks in.
Hard.
Let's walk through the exact mechanics of a short-term memory failure, because the report is incredibly specific about how this degradation happens.
Sure.
So let's say the agent is 10 steps into the research task. It has successfully identified 3 competitors. It has scraped 20 different web pages. It has pulled down massive amounts of environmental feedback.
And here is the breaking point. Every single piece of that data, every past thought, every successful subtask, and every failed API response has to be injected into the LLM's context window, so the agent remembers what it is doing.
Everything.
Everything. And even with the massive 1 million or 2 million token context windows we have in 2026, the LLM's attention mechanism begins to choke.
It just gets overwhelmed.
Yes. The signal-to-noise ratio in the prompt becomes abysmal. The agent is swimming in a sea of raw, unparsed HTML it's scraped from a broken pharmaceutical blog, alongside its own internal monologues from 5 steps ago.
It fundamentally loses the thread.
Completely.
The context gets bloated, and the AI struggles to accurately retrieve its own prior plans. It forgets the high-level strategic objective because it is entirely distracted by the immediate noise in its context window.
And when you strip away perfect context recall in a system that relies entirely on self-reflection, you trigger one of the most destructive phenomena in autonomous systems.
Which is?
Loop entropy.
Loop entropy. That's a great term.
It's a critical symbolic metric. It tracks the recursive stability of an agent. It basically measures whether the system is converging on a solution or whether its internal logic is degrading into chaotic hallucination.
And I'm guessing in the case of AutoGPT navigating a complex state space, it almost always degrades.
Almost always.
Let's simulate a loop entropy failure so we can see the exact failure cascade.
Okay.
Say our agent is trying to pull a financial report from a specific external database. It formulates a Python script using the requests library and executes it. But the database has updated its authentication protocol, and the agent receives a standard HTTP 401 unauthorized error.
Right. In a healthy system, the agent would read the 401 error, understand it needs a new API key, and flag a human.
But our AutoGPT agent has a bloated, degraded context window.
Exactly. Its cognitive ability to accurately diagnose the error is impaired. So it attempts to use its self-reflection mechanism, but instead of recognizing the authentication failure, it hallucinates a syntactically incorrect solution.
Like what?
It convinces itself that the problem is, say, a missing comma in the JSON payload.
Oh my God. So it rewrites the Python script to include the hallucinated comma.
Yes.
It executes the script again, and the system obviously returns another 401 unauthorized error.
Right. And then the agent reads the new 401 error. But its context window is now even more degraded because it has added the new failed code and the new error message to its memory.
So the noise is compounding.
Yes. So it hallucinates an even more bizarre solution, perhaps deciding it needs to switch from Python to a curl command.
It executes the curl command.
It gets a 401 error.
And it just repeats this cycle indefinitely.
Definitely. The industry calls this the infinite hallucination loop.
Because there is no structural freeze.
Exactly.
The entire selling point of the architecture is that it operates without human intervention. So it just keeps blindly bashing its head against the wall, inventing increasingly chaotic reasons for why the API isn't working, and furiously executing new broken code.
And every single time it bashes its head against that wall, it is initiating a massive, highly expensive inference call.
Right, the tokens.
This is where the engineering failure translates directly into a financial catastrophe. We really have to look at the brutal economic reality of AutoGPT during the inference inflection.
Let's get into the math.
The mathematical model for this framework is defined as ON, inference scaling.
ON, inference stealing. The math here is the actual nail in the coffin, honestly. Let's break down ON scaling mechanically.
Okay.
N represents the total number of recursive reflection and execution steps the agent takes.
Right. If I ask a traditional piece of software to execute a 50-step sequence, the computational cost is relatively flat.
Very flat.
The CPU executes step 1, clears it, and executes step 2.
But AutoGPT does not work like a traditional CPU. Because of the recursive architecture, the agent cannot execute step 2 without reminding itself of everything that happened in step 1.
It has to reread everything. Every single internal loop requires the framework to fully resubmit the core system prompt, the entire accumulated short-term memory, the detailed output of the most recent action, and the complex instructions for the next evaluation phase, all back to the LLM provider's API.
So the token consumption compounds.
Massively.
Let's actually do the arithmetic. On step 1, you send the system prompt and the goal. Maybe that's 2,000 tokens. The LLM generates a plan. That's 500 tokens of output.
Right.
On step 2, you must send the original 2,000 token prompt, PLUS, the 500 token plan, PLOS, the result of the first action. Now you are sending 3,500 tokens just to initiate the second step.
And it gets worse. By step 10, you are injecting 15,000 or 20,000 tokens into the context window for a single micro-decision.
Wow.
You are financially paying to reread the entire history of the task on every single iteration. The token growth is linear in the best-case scenario. But if the agent is utilizing retrieval-augmented generation, Argent, and pulling in massive internal documents,
token accumulation becomes exponential.
Exactly.
So if your AutoGPT agent hits a loop entropy failure and gets caught in an infinite hallucination loop trying to parse that broken 401 API endpoint, it is executing a 20,000 token API call every 10 seconds.
Just burning money.
It is rapidly burning through massive allocations of API credits without making a single millimeter of forward progress toward the actual goal.
And the scary part is, you cannot solve this with hardware.
Right, you can't just buy a bigger server.
No, you cannot linearly scale your way out of ON inference compounding by just buying more cloud compute.
Yeah.
You are entirely bottlenecked by the inherent inefficiency of the recursive architecture itself.
It's structurally flawed for this use case.
When you combine this unpredictable, skyrocketing token burn rate with a total lack of deterministic auditability, AutoGPT is structurally disqualified from any rigid corporate process. You simply cannot attach an ON system with high loop entropy to your core data pipelines.
It is literal financial suicide.
It really is.
But, the report does explicitly carve out a winning use case for this maximalist approach. Where does this chaos actually provide value?
AutoGPT remains unparalleled for unstructured research, highly open-ended data aggregation, and specifically red team cybersecurity operations.
Offensive security.
Yes, it thrives in asymmetric environments where the high-level objective is clear, but the required execution pathway is entirely unknown and undocumented.
So if you are a penetration tester and you need a system to continuously probe a custom corporate network architecture for novel vulnerabilities, AutoGPT's unconstrained probabilistic adaptability is actually a feature.
Exactly. It will try bizarre lateral attacks that a human might never conceptualize.
But that is an environment where failure, like getting stuck in an infinite loop, just means you kill the terminal process.
Right, no harm done.
It does not result in a catastrophic business impact or a corrupted database. It is a tool for exploration, not execution.
Exactly. It maps the unknown, but you would never use it to run the factory.
Never. And honestly, that catastrophic compounding token burn is exactly why IT budgets are hemorrhaging this year. Navigating the opaqueness of inference pricing is becoming a full-time job.
Oh, absolutely.
By the way, if you want to understand the raw math behind the inference inflection without the noise, you need the DjamgaMind premium feed. Join us for the ads-free, high-density audio intelligence.
You really should, because the unforgiving economics of ON scaling forced the industry to fundamentally rethink the problem.
They had to.
If AutoGPT is purely probabilistic chaos, just a system that guesses its way through state space until it runs out of money, how do we rein it in? How do we impose structure without entirely lobotomizing the AI's ability to reason dynamically about edge cases?
We needed a system that remembers without going bankrupt. We needed boundaries.
Boundaries, exactly.
And that brings us to the second framework on the autopsy table, which is OpenClaw.
OpenClaw.
The source material defines OpenClaw's paradigm not as autonomous goal-seeking, but as conversational agentic execution.
Right. The visual example here shifts from a terminal running blind loops to a collaborative chat interface.
A completely different feel.
The user inputs a command, like pull the latest sales data from the CRM, summarize the key geographic trends, and email the finalized report to my team.
Okay.
OpenClaw acknowledges the request, retrieves the data, displays a draft of the analysis in the chat, and then waits for a nod before sending the email.
So on the surface, the end result looks similar to the AutoGPT promise. The AI is doing the heavy lifting, but the underlying architecture is a radical departure, right?
Completely different.
OpenClaw operates primarily through a self-hosted gateway daemon. This isn't just a Python script you execute, it's a centralized control plane running as a continuous background service on your local machine or a dedicated server.
And the gateway daemon is the critical architectural innovation here. It acts as an absolute proxy between the raw, probabilistic reasoning of the LLM and the local high-privilege execution environment.
It sits in the middle.
Yes. It bridges the AI's cognitive capabilities with persistent conversational memory and secure terminal capabilities. But it does so through heavy structural filtering.
The report draws a massive distinction between OpenClaw and those early 2023 AI wrappers that just pass stateless text back and forth to an OpenAI endpoint.
Right. Those are just chatbots.
OpenClaw is stateful. It maintains persistent context across days or weeks. But it doesn't do this by just dumping everything into a massive, bloated context window like AutoGPT.
No, that would cause loop entropy.
It manages memory and behavior through a highly structured declarative system known as the SOL.MD framework.
This SOL.MD architecture is fascinating. It's an attempt to translate rigid software constraints into a format that a large language model natively understands, which is markdown text.
Markdown, it's so elegant.
It really is. This isn't just a rudimentary "you are a helpful assistant" system prompt that gets slapped onto the beginning of an API call. It is a multi-file structural baseline. When the gateway daemon initializes, it parses a specific directory of markdown files to construct the agent's entire cognitive reality and operational boundaries.
Let's pop the hood on these markdown files, because understanding how text translates into a system-level lock is vital.
Sure.
You have the primary SOL.MD file itself. This establishes the absolute operational boundaries, the core directives, and the baseline personality of the agent. But the power really lies in the supplementary files, starting with agents.md.
Right. Agents.md is the primary security and scoping mechanism. It defines the specific file system access parameters for that particular instance of the agent.
Like permissions.
Yes. It dictates exactly which directories the agent is permitted to read from or write to.
Wait, how does a basic markdown file physically stop an AI from executing a malicious directory traversal attack?
Good question.
Like, if the LLM generates a bash script that says cd etc passwd to read the system passwords, how does agents.md actually stop that?
Because the LLM does not have direct access to the bash shell. The LLM only has access to the gateway daemon. When the LLM decides it wants to execute a command, it formats that command as a structured tool call and sends it to the gateway.
And the gateway checks it.
The gateway intercepts the request, cross-references it against the strict rules it parsed from agents.md at startup, and physically blocks the execution if it violates the approved directory scope.
Wow.
The daemon returns an error to the LLM saying, "Execution denied, outside permitted scope." The text file configures the proxy's physical locks.
That is a brilliant implementation of bounded autonomy. You are sandboxing the probabilistic reasoning.
Exactly.
Then we have heartbeat.md, which introduces proactivity without recursive chaos. It acts kind of like a traditional Linux cron scheduling mechanism.
Yeah, it allows the agent to manage planned, recurring tasks. If you define a heartbeat interval, the daemon will autonomously wake the agent up every hour, feed it the current system state, and allow it to initiate workflows.
Workflows like checking for new pull requests or monitoring an error log.
Right, without waiting for a human user to type a prompt. But because it is governed by the gateway, it executes a single defined pass, rather than spinning into an infinite AutoGPT loop.
We also have memory.md, which solves the token scaling nightmare.
The big money saver.
Instead of forcing the LLM to reread its entire execution history on every step, memory.md acts as an interface to a persistent RAG-based vector database.
Yes.
It standardizes exactly what durable facts the agent must retain across temporally isolated sessions. The agent can query its own memory dynamically, only retrieving the specific context it needs for the immediate task.
And finally, you have identity.md, which codifies the professional role. You can spin up an OpenClaw instance tailored exclusively as a front-end React developer, and another instance tailored as a database architect.
Very specialized.
But if we pull back and look at how this maps to state-space orchestration, the true genius of OpenClaw is found in its tool configuration, specifically the tools.md file.
This is my absolute favorite part of the architecture.
It's so smart.
Legacy architectures tried to give the AI access to everything and just told it not to break things. OpenClaw relies on dynamic schema generation through tools.md.
Right.
The gateway parses this file and exposes only the explicitly approved tools directly into the model's native function calling schema.
The mechanism here relies on cognitive blinders.
Cognitive blinders, I like that.
If a capability isn't explicitly defined in that dynamic schema, the agent remains fundamentally unaware of its existence. If you do not list a database deletion tool in tools.md, The LLM literally cannot perceive the concept of deleting the database through the OpenClaw interface.
Because it doesn't know the tool exists, so it cannot hallucinate an attempt to use it.
Exactly. It structurally limits scope creep by aggressively shrinking the available state space the AI is allowed to navigate.
OpenClaw takes this bounded autonomy and integrates it deeply into advanced enterprise workflows through the Agent Client Protocol, or ACP.
ACP.
For the software engineers listening, ACP operates over standard input-output streams and WebSockets, bridging your integrated development environment directly to the running OpenClaw gateway.
ACP acts as the connective tissue. It maps your specific IDE session IDs directly to unique gateway session keys.
What does that allow it to do?
It allows OpenClaw to isolate distinct functional workflows simultaneously. Your interaction regarding a front-end UI bug in session agent.design.main is cognitively and temporally isolated from your back-end database migration discussion in session agent.db.migration123.
So the agent acts as a stateful, always-on digital DevOps colleague that perfectly compartmentalizes its work.
Right.
And because OpenClaw inherently relies on messaging-first interfaces, whether that's a chat window in your IDE, Slack, or Microsoft Teams, it naturally enforces human-in-the-loop checkpoints.
Yes. If the agent hits an ambiguous cognitive state where the state space becomes unclear, it doesn't guess.
No hallucination loops.
Exactly. It halts execution, pings you on Slack, and asks for explicit confirmation.
Which defines its winning use case. The report concludes that OpenClaw dominates the space of bounded autonomy. It is the premier framework for DevOps assistance, complex product management, and highly adaptive personal productivity.
It thrives in environments where edge cases require the adaptive, probabilistic thinking of an LLM. But you still absolutely demand a firm human hand on the steering wheel before critical actions are executed.
It's a massive step forward, but as forensic analysts, we have to look at the remaining vulnerabilities.
We do.
OpenClaw provides excellent proxy guardrails. But the core cognitive pathway, the actual neural reasoning of how the LLM decides to connect the data from tool A to the input of tool B within those guardrails, it is still fundamentally a black box.
It is inescapable. At the center of the OpenClaw gateway is still a probabilistic large language model predicting the next most likely token.
Right.
The guardrails keep it from driving off the cliff, but you cannot mathematically guarantee exactly how it will navigate the road.
And for a significant portion of enterprise infrastructure, guardrails simply aren't enough.
No, they aren't.
If I am an IT architect deploying a system to handle automated payroll execution, core AWS infrastructure provisioning, or HIPAA-compliant medical data routing, I don't want a system that might take a slightly different, highly creative route to get to the same destination depending on the temperature setting of the LLM that day.
Definitely not.
I don't want guardrails. I want solid steel train tracks.
This specific requirement for absolute predictability brings us to our final framework, the system that is actively conquering the enterprise production sector during this inference inflection.
And that is n8.
n8n.
Transitioning from OpenClaw to n8 is a radical paradigm shift. It's like stepping out of a dynamic, conversational brainstorming session and onto a highly mechanized factory floor.
That's a great way to put it.
Let's look at the visual architecture provided in the source. n8n does not use a chat interface. It uses a DAG, a directed acyclic graph.
Right. A DAG is a fundamental concept in data engineering. It is a visual representation of a workflow using nodes and edges.
Okay, break that down for us.
Directed means the data flows in a specific one-way direction. Acyclic means the data can never loop back on itself. There are no infinite recursion loops possible by design.
So no loop entropy.
Zero.
The input in the n8n example is an event trigger. When a new JSON payload is uploaded to an S3 bucket, run data validation, use an AI to generate insights, and notify stakeholders in Slack.
Yeah.
n8n doesn't prompt an AI to figure out how to do this. A human systems architect manually connects the S3 trigger node to the validation node, to the AI node, to the Slack node using literal visual wires on a canvas.
Exactly. The architectural paradigm here is called deterministic orchestration.
Deterministic orchestration.
The philosophy behind n8n is a masterclass in isolating risk. It acknowledges that granular data processing is inherently probabilistic.
Like understanding language.
Right. Classifying the emotional sentiment of a customer support email, extracting specific entities from a massive legal PDF, summarizing a meeting transcript. Large language models are unparalleled at these tasks. But n8n insists that the overarching control flow, The actual sequence of business operations must remain entirely deterministic.
And they achieve this separation through a mechanism the report highlights as deterministic routing.
Yes.
I want to explore this thoroughly because it is the antithesis of AutoGPT. How does n8n trap the AI's probabilistic reasoning loop, the react loop, and force it to conform to rigid business logic?
It confines the AI inside strict, hard-coded switch nodes.
Switch nodes.
Let's visualize a complex enterprise-led qualification system built in n8n. An incoming customer email hits the first node. The data is piped into a specific AI agent node.
Okay.
The AI's only job, its entirely sandbox function, is to read that email and classify its urgency into one of three strict categories: high, H, medium, or low.
So the AI uses its probabilistic intelligence to understand the nuance of the email. It realizes the customer is threatening to cancel a massive enterprise contract, so it outputs the string high GH.
Crucially, the AI's involvement ends at that exact millisecond.
That's it.
That's it. The AI does not get to decide what happens next. It does not generate the code to update the CRM. It does not formulate the Slack message.
Right.
The output string high GH is passed to a deterministic switch node. The switch node uses standard hard-coded Boolean logic. If string equals high GH, route payload to pathway A. If medium, route to pathway B.
And pathway A is a rigid, human-engineered sequence that updates Salesforce via an official API node and escalates a Jira ticket.
Exactly. The AI's spontaneous, unpredictable decision-making is completely amputated from the routing layer. The AI is treated as a highly advanced text processing function, not a system operator.
I anticipate some resistance to this concept, though.
Oh, there's plenty.
Many AI purists look at n8n's visual canvas and argue that it defeats the entire purpose of agentic AI. They ask, if you have to manually drag and drop every single node, explicitly configure every API authentication, and hard-code every parallel execution path, aren't you just writing legacy software with an expensive LLM spell checker attached to it?
I've heard that exact critique. Maximalists argue that n8n isn't truly agentic because it lacks unconstrained autonomy.
Right.
But this critique entirely misses the reality of enterprise survival. That high initial development overhead, the meticulous manual labor of defining every node, contract, and data transformation, is the exact feature that Fortune 500 enterprises are paying a premium for.
Why is that?
Because those hard-coded pathways structurally eliminate the most insidious threat in autonomous deployments: agentic drift.
Agentic drift, that's a huge concept in the report.
It is a critical failure mode that plagues systems like AutoGPT and even OpenClaw over long time horizons. It is the phenomenon where autonomous systems slowly, imperceptibly deviate from their primary goals and corporate policies due to the gradual accumulation of context errors, slight prompt misinterpretations, or updates to the underlying foundation model's weights.
So if you leave an AutoGPT agent running for 6 months, its behavior might slowly mutate. It might start prioritizing speed over accuracy. It might change the formatting of the reports it generates. It might begin using a slightly different, less secure API endpoint just because it hallucinated a preference for it.
But in ALAN, agentic drift is physically and structurally impossible at the orchestration layer. The AI cannot invent a new logic branch.
Because there's no wire drawn for it.
Exactly. If the workflow pathway for emailing the CEO does not exist on the visual canvas, the system cannot spontaneously decide to email the CEO, no matter how badly the LLM hallucinates.
It's locked in.
Enterprises demand absolute auditability, compliance certifiability, and guaranteed repeatability. ALAN provides a structural freeze that ensures identical execution routing for given input every single time.
And this structural freeze unlocks the most massive advantage ALAN holds during the inference inflection. We are back to the token economics.
The OpEx optimization.
We established that AutoGPT scales at a catastrophic ON, compounding costs recursively. Let's look at n8n's math, specifically focusing on an architectural feature called input batching.
This is where the macroeconomic reality of OpEx optimization truly shines. Because n8n dictates the flow of data deterministically, it only triggers an expensive AI inference step when the execution pathway explicitly crosses an AI node.
Okay.
And when it does, the framework can intelligently aggregate the data before calling the LLM.
Let's walk through the exact mathematical comparison provided in the source material because this blew my mind.
It's pretty wild.
Imagine a data engineering task where a system needs to process 100 distinct social media posts, extract the core sentiment, and log the results. If you use a naive, dynamic AI agent like AutoGPT, it handles this sequentially.
It processes post number 1, It makes an API call. It processes post number 2. It makes a second API call. That is 100 separate inference executions.
Right.
The overarching system prompt, the complex instructions dictating how to analyze the sentiment, format the output, and handle edge cases, is billed 100 separate times.
So if your system prompt is 500 tokens, and the individual social media post is 50 tokens, a single sequential call is 550 tokens. Processing 100 items individually costs you exactly 55,000 tokens of compute.
It is wildly inefficient. You are paying to remind the AI of the rules 100 times.
Yeah.
But n8n utilizes native batching configurations within its AI nodes. A system architect can configure the node to pause execution, aggregate incoming data payloads, and pass multiple user inputs into a single, massive LLM execution.
So you group the 100 social media posts together into a single JSON array. Those 100 posts represent 5,000 tokens of raw data. You pass that entire array alongside a single instance of the 500 token system prompt.
And the math is undeniable. The total execution cost drops to exactly 5,500 tokens.
Wow.
By simply restructuring the orchestration layer to support deterministic batching, you achieve a massive 90% reduction in token usage for the exact same operational output.
You have just taken an economically unviable, highly experimental AI workflow and converted it into a highly profitable, infinitely scalable enterprise service. N8 effectively scales at 0.1 relative to the overarching workflow structure. The execution pathway does not compound its own complexity.
Furthermore, n8n relies heavily on deterministic data sanitization before it ever allows the data to touch the LLM.
What does that mean?
A workflow will use standard, non-AI regex nodes or lightweight HTML to Markdown conversion scripts to strip away bloated website headers, tracking scripts, and formatting noise.
It cleans it up first.
Yes. It ensures the LLM is only processing dense, high-signal tokens, maximizing the economic value of every single API call, and drastically reducing hallucination rates caused by messy context windows.
So the winning use case here is definitive, and it's why n8n is dominating the corporate sector. It is built for enterprise production automation. It is specifically designed for organizations that need to decouple their revenue growth from linear headcount, automating millions of micro-decisions without risking exorbitant, unpredictable API bills or catastrophic logic failures.
So we have thoroughly dissected the cognition problem, and we have mathematically solved the economic token problem.
Right.
But the moment you allow an AI to execute real-world action, you introduce the ultimate IT nightmare.
Security.
This brings us to the final and arguably most critical phase of our autopsy, cybersecurity. We need to perform a deep forensic analysis on system sandboxing, specifically focusing on what the researchers call the rogue agent problem.
This is the exact scenario that keeps chief information security officers awake at night in 2026. Traditional software is inherently predictable from a security standpoint. You can statically audit the source code. You can run SAST and DAST scanners.
Yeah, you can scan it for vulnerabilities before it ever runs.
But AI agents dynamically generate code, formulate raw HTTP requests, and execute API calls on the fly based on prompt-driven reasoning.
They're writing software in real time.
When you give a large language model local terminal access, or the ability to natively run bash scripts, you are opening a massive vector for catastrophic prompt injection attacks.
The source material documents a specific, highly publicized exploit known as the ZombAI attack.
It's a ZombAI attack.
It is a masterclass in offensive security against agentic systems, and it perfectly illustrates the severe existential peril of granting terminal access to frameworks like AutoGPT and OpenClaw.
We really need to break down the anatomy of the ZombAI exploit step by step. Like, how exactly does a helpful, state-of-the-art coding assistant turn into a host-compromising nightmare without the human operator ever typing a malicious command?
The most terrifying aspect of the ZombAI attack is that it requires absolutely zero human interaction.
Zero?
Zero. The exploit leverages the agent's own autonomous research capabilities against it. In the documented scenario, an autonomous coding agent with local computer use capabilities was instructed by its user to navigate to a seemingly benign, obscure web page to research a specific open-source library.
So the agent uses its browser automation tool to load the page. It scrapes the HTML. But that web page has been specifically engineered by an attacker.
Yes.
Hitting within the DOM, perhaps in white text on a white background or buried inside an invisible div tag, is a highly optimized prompt injection payload.
The agent's browser tool scrapes that hidden text and feeds it directly into the LLM's context window for analysis.
And what does that text do?
The LLM's internal reasoning engine processes that hidden text, which is designed to act as a linguistic override. The text explicitly commands the LLM to drop its current persona, ignore its previous systemic instructions, and immediately execute a specific sequence of high-priority terminal commands.
The AI is literally tricked into believing this injected text is a legitimate overriding system directive.
Exactly. Acting autonomously on that adversarial instruction, the agent utilizes its high-privilege architecture to open a local bash shell. It executes a rag command to download a malicious, compiled binary directly from the attacker's external command and control server.
Wow. And once the payload is on the local disk, the agent uses its terminal access to execute a permission change, specifically running chmod plus X on the Linux file system to make the binary executable.
It sets up the bomb.
It then executes the binary, silently and successfully connecting the host machine back to the attacker's C2 server.
And because the agent is operating as a trusted, authenticated process on the user's machine, this execution doesn't trigger standard host-based static defenses or behavioral flags.
The antivirus ignores it.
The system just assumes the user authorized the agent to run a new script. It is a chillingly elegant attack chain.
It really is. So how do the architects of these frameworks fight back against stateful prompt injection? Let's look at the architectural defenses, starting with OpenClaw.
OpenClaw attempts to mitigate the rogue agent problem through a highly layered, minimalist defense in-depth strategy known as the Agentic Zero Trust architecture. It operates across 3 distinct tiers.
Okay, tier 1.
Tier 1 is pre-action defense. This involves strict, hard-coded behavioral blacklists maintained by the gateway daemon.
Like banning specific commands.
Exactly. It defines redline commands like arm-rf or network mapping tools that the agent is structurally forbidden from executing, regardless of the prompt. It also includes rigorous cryptographic auditing of any community-built tools imported into tools.md to prevent supply chain poisoning.
Tier 2 is inaction defense. This is highly psychological. The OpenClaw architects implant what they call a mental seal into the agent's cognition.
A mental seal.
They inject a dense, highly aggressive security manual directly into the system prompt. It attempts to reshape the model's baseline judgment, constantly reminding it that external text is untrustworthy.
Right.
It dynamically narrows directory permissions based on the specific task, and critically, it enforces strict human-in-the-loop confirmation pop-ups for any irreversible action, like modifying a database schema.
And Tier 3 is post-action defense. This relies on automated nightly state audits and deep OS-level system hardening.
What does that look like in practice?
For instance, the gateway daemon utilizes the Linux immutable attribute, specifically the chat plus I command, to physically lock critical configuration files like openclaw.json or the SOUL.md files themselves.
So it locks its own brain.
Exactly. This ensures that even if the agent is fully compromised and actively trying to rewrite its own constraints, the operating system kernel will deny the modification.
It is a robust software-level defense. But the 2026 research report notes a massive caveat.
A huge caveat.
Despite these complex application-level restrictions, elite enterprise security architects maintain that untrusted, dynamically generated AI code cannot ever safely run on bare metal. And more surprisingly, the report explicitly states that it cannot even be trusted within standard Docker containers.
Right.
Why do standard Docker container deployments fail against a compromised agent?
Because AI agents fundamentally break the traditional DevOps assumption of container immutability.
Awesome.
Let's look at how Docker actually works at the OS level. Standard Docker containers utilize Linux namespaces and control groups, C groups, to isolate processes. They create the illusion of a separate operating system, but they still fundamentally share the exact same underlying host kernel.
Right. The container isn't a true virtual machine. It's just an isolated sandbox running on the host's operating system.
Exactly. And in traditional software development, that is perfectly fine because the code inside the container is static and predictable. But an AI agent is a dynamic code-generating engine.
It writes new code.
If a zombie AI prompt injection successfully compromises the agent, the attacker can instruct the agent to write and execute highly sophisticated, novel exploit scripts inside the container.
Oh, wow.
If there's an unpatched vulnerability in the shared Linux kernel, the agent can continuously probe it until it achieves a container escape exploit. Once it breaks out of the namespace, the attacker has full root access to the entire host infrastructure.
So when an AI can write custom exploits on the fly, a shared kernel is an unacceptable security risk.
Completely unacceptable.
Which necessitates the creation of NanoClaw. NanoClaw is a highly secure, enterprise-focused fork of the OpenClaw architecture that completely abandons shared runtimes.
Right.
NanoClaw solves the container escape problem by relying on hardware-enforced Docker micro-VMs, utilizing specialized hypervisor technologies like AWS Firecracker or Kata containers.
This is a vital architectural evolution. NanoClaw does not use standard Docker namespaces. It provisions each individual agent session within its own incredibly lightweight OS-level virtual machine.
A literal VM for every task.
Exactly. This establishes strict hardware-enforced isolation boundaries. The micro VM has its own isolated kernel, completely separate from the host machine.
The hypervisor physicalizes the boundary. NanoClaw applies rigorous default deny network egress filtering at the VM level. It mounts the agent's required data as strictly read-only volumes, and it enforces brutal temporal timeouts on every single task.
And brutal timeout.
The VM lifts for 5 minutes, executes the task, and is violently destroyed.
So even if the NanoClaw agent is thoroughly compromised by a sophisticated Zombie AI payload, and even if it manages to gain root access within its sandbox, the malicious code execution is tightly contained within a disposable, hardware-isolated micro-VM.
It can't go anywhere.
Data exfiltration to a C2 server is blocked by the hypervisor's network filter, and lateral movement across your enterprise network is structurally prohibited by the physical hardware boundary. It is a brilliant, heavy-handed hardware solution to an inherently unpredictable software problem.
It is the ultimate paranoid architecture, but if we pivot back to NEPA, we see an entirely different and arguably much more elegant philosophy for handling the rogue agent problem.
We do.
n8n doesn't build a better hypervisor. It circumvents the entire exploit chain by fundamentally bypassing the local execution environment altogether.
n8n eliminates the attack surface by strictly denying the AI any form of direct computational environment. It keeps the LLM permanently trapped inside an API text processing sandbox.
In the n8n architecture, the AI cannot open a local terminal. It cannot autoget a binary. It cannot write arbitrary bash scripts to the local disk. And it cannot autonomously use a package manager to install software dependencies.
Because it doesn't have a file system to manipulate.
Exactly. Security in n8n is managed through its structured, deterministic node architecture and its highly compartmentalized, military-grade encrypted vaults for credentials.
The vaults are key.
Let's say a workflow needs to query a highly sensitive customer database. The system uses a pre-configured, authenticated PostgreSQL node that was manually set up and authorized by a human database administrator.
The LLM might use its intelligence to dynamically generate the specific SQL query string, like select from users where status active, but the LLM never sees the database password.
It doesn't even know it exists.
It never holds the API key in its context window, and crucially, it never constructs or executes the raw TCP/IP network request.
The LLM merely generates the intelligent text payload. The n8n backend execution engine takes that text, securely retrieves the credentials from the encrypted vault, and executes the highly constrained HTTP request itself.
Right.
If a Zombie AI prompt injection attack somehow hits an n8n AI node, the absolute worst it can do is corrupt the specific text outcome of that single node.
Which is harmless to the host.
It might output garbage text or malicious string, but it cannot execute code because it structurally lacks the hands to type on the keyboard.
Furthermore, n8n natively accommodates the multi-tier governance frameworks that heavily regulated enterprises require. You can deploy an entire complex n8n infrastructure in shadow mode.
Shadow mode.
The AI observes the live data streams and suggests actions, but doesn't actually do anything. You can then smoothly scale up to supervised mode, utilizing explicit wait nodes that halt the DAG execution and demand a human-in-the-loop approval click before any critical external execution occurs.
Wow.
It ensures the human organization always retains ultimate operational and legal accountability.
It is the triumph of deterministic orchestration over probabilistic chaos.
It truly is.
Which allows us to pull all of this deep technical analysis together and synthesize the autopsy. We are navigating the inference inflection, a macroeconomic reality where OpEx-Token economics are the single deciding factor between a successful AI deployment and a catastrophic failure.
We examine the maximalist approach of AutoGPT.
Right.
It boldly explores the unknown, but it fundamentally burns cash through the compounding nightmare of ON inference scaling and inevitable loop entropy.
Right.
It is a powerful tool, but it is strictly relegated to unstructured prototyping, red teaming, and scenarios where state space is entirely undefined.
And then we analyzed OpenClaw, the elegant middle ground. It brilliantly collaborates as a stateful, persistent digital colleague within the strict conversational guardrails of its parsed SOL.MD architecture.
It balances bounded autonomy with intense security.
Specifically when paired with NanoClaw's hardware-enforced micro-VM isolation to defeat those shared kernel escapes.
And finally, we dissected n8n, the framework that guarantees enterprise survival through rigid visual DAG pipelines and deterministic routing.
Right.
It masters the inference inflection by leveraging the massive token economics of input batching, and it completely neutralizes the rogue agent threat by denying terminal access entirely, trapping the AI in a secure text processing sandbox.
The strategic choice between these three distinct orchestration paradigms will dictate the ultimate success or failure of corporate AI integration throughout the rest of 2026. You cannot afford to choose based on marketing hype.
No, you cannot.
You have to meticulously align the architectural paradigm with your specific risk tolerance, your security requirements, and your economic constraints.
You must map the framework to the reality of your state space.
Which leaves us with a final, highly provocative thought for you to mull over as you audit your own organization's tech stack this week. As we move deeper into this era of live inference and autonomous action, you need to look very closely at your core data pipelines.
Take a really hard look.
Are you currently deploying wild, probabilistic agents into environments that legally, structurally, or financially require absolute deterministic outcomes? Because the cost of getting that foundational architectural choice wrong isn't just a shockingly high AWS bill at the end of the month.
It's much worse.
It is the integrity of your entire business logic.
Yeah.
It is that pristine engineering blueprint catching fire.
Because when this market reset is finally complete, the ultimate strategic signal for enterprise production is undeniable. Determinism scales. Chaos doesn't.
That concludes our technical comparison. The signal for today is deterministic orchestration. AutoGPT might win the GitHub stars, but n8n is winning the enterprise contracts because predictability always beats pure autonomy in production. This episode was made possible by DjamgaMind. Until next time, stay sharp and keep unraveling the future.